That's me. Hold on.
I don't understand how this thing is. These are not instructions, just tell me what buttons do what. I couldn't tell.
That's what instructions are. These are instructions.
Yes. Alright, so as the wavelength goes down, the energy goes up because it's a more excited wave that's moving faster, shorter wavelength. Radio region of the electromagnetic spectrum will have which of the following molecular effects? So the radio wave is going to do the nuclear spin transitions. So that would be our NMR, and we use radio wave to do those transitions.
It's nuclear spin, so it spins on rotation.
Okay, which of the following methods would be used to determine the relative amounts of each element in a sample? So we're looking at the relative amounts, it's going to be combustion analysis. Sodium fusion is going to tell us what kinds of other elements we have, like sulfur or nitrogen or the halogens. And then mass spectrometry will give us the mass, and then we can compare stuff, but we don't get the relative amounts. See if you've been practicing. Which of the following is the correct formula for calculating the hydrogen deficiency index? Formula is adding one nitrogen and subtracting one halogen with the 2n plus 2, and then you divide the whole thing by 2. So which of the following is the correct formula for using the rule of 13?
One person.
N, or Cn, and then H, the N plus the R, numerator plus the remainder. Now let's see if you can apply it. You'll be able to do this one in your head.
Does squeaking help you get the answer?
So that would be 13 times 2, right? It's 26. Plus 2, so it would be a 2, remainder 2. And so you have C2H, 2 plus 2 is 4. P is the correct answer. Which of the following are not considered not a P in an IR spectrum?
I'm sorry, wave number.
Alright.
Oh. Yay! I was going to be really concerned for that.
So, go look at the color of the P. Which of the following CH stretches will be below 3,000 centimeters in this one? The hydrogens are all indicated, so carbon, hydrogen, etc. So, CH would be an sp3 hybridized carbon. A hydrogen would show up below 3,000. So A would be the correct answer. The others are sp2 and sp hybridized, which show up above 3,000.
So like the aromatic, that's not at like 1,614.
That would be the carbon-carbon
so
stretches, but we're looking at the CH on this one in particular. It says CH right there. Alright, mass spectrometry can give information on the elemental composition of a molecule. True or false?
What do you call classification?
What do you qualify as information?
Any.
Anything?
Oh, like any?
I know.
I misunderstood. Pick some
Alright, you're all in. Obviously talking about it. That quiz takers. Yes, it is true that you can get elemental composition of a molecule from mass spectrometry. So what is the difference here? We've got combustion analysis, which will tell us relative amounts of the different atoms. The mass spectrometry is going to give us some information about it, and we can actually get numbers in terms of some of the elements that we'll look at, but it's not going to give you an exact ratio of carbon to hydrogen, say. That you get from combustion. Okay. And you get a point for showing up.
Oh, what do I need to read?
So we are going to finish up where we were on last time we were here Monday. And so that was the UV Viz. And then today we're going to start in on the mass spec, probably get to a little bit of NMR. We're going to focus on carbon today. And then on Friday we'll finish up NMR, carbon, and proton. All just a quick review of what we've learned in other classes. visible spectroscopy or UV vis. And we said that we would look at lambda max as a key feature and epsilon as a key feature. And so if we look at this spectrum, we see the peak absorbance here is at 242.5 nanometers, and its epsilon is 13,100, and that's for this 2,5-dimethyl 2,4-hexadiene shown there. You'll see that we don't get very interesting peaks in UV vids. Usually you'll get one, maybe two or three peaks, and they don't tell you a whole lot about the structure of the molecule. But we will use them to look at some aromatic systems and other conjugated pi-bond systems. One thing that they can give us is the ability to do some calculations to determine concentrations of samples if it's an unknown, or to figure out this epsilon. So your first sample you would want to make, if you did not know what epsilon would be, you would want to make up a known concentration of your sample so that you can then measure the epsilon. The epsilon comes from the absorbance divided by the concentration times length. So let's define all these terms here. Lambda max is going to be the wavelength at the top of the peak. Which would be the maximum absorbance. And A is our absorbance. And then we have epsilon, which is our molar extinction coefficient, or the molar absorptivity. C will stand for our concentration, and that should be moles per, let me double check, I think it's per. Yeah, the molar concentration, moles per liter. And length, L stands for the length of the tube, or the cell, in centimeters. So lambda max doesn't go into our equation, but it's how we determine what A is going to be. A is going to be the absorbance at the lambda max. And then we are going to use our concentration if we know it, and the length of our cell to determine epsilon. Epsilon is known for a lot of common molecules, and so then you can also use that as a way to calculate concentration of an unknown sample. If you knew epsilon, you know the absorbance, and you know the length of your tube, you can calculate for concentration. And you use the Beer's law equation for that. And yeah, we don't need to do a calculation, do we?
No,
Okay.
I can't figure out how to multiply things.
But where does that show up? We're going to go into these in more depth, but the Woodward-Fisher rules, they took all sorts of different conjugated systems and took the UV vis and then found commonalities between them. And then actually the wavelength of your maximum lambda max is going to increase by pretty specific increments depending on what is substituted on the diene. So they take the standard sample, being a conjugated diene with two double bonds in a row, and that tends to absorb at 217 nanometers. If you add additional double bonds, for each additional double bond, it adds about 30 nanometers to the wavelength. So if we have 2 on this example, we would start with 217 nanometers. We would add in 2 times 30, which would be 60, and we would get 277 nanometers as the wavelength at which this would absorb. Turns out this is actually 290, so it's close to where it's absorbing, but not quite exactly there. Alkyl groups can increase it, so if you have an alkyl group directly attached to the diene, there's 3 of them on this one, so it's going to be 217 nanometers. 3 times 5 is going to be equal to 15 nanometers. And that's going to give us 232 nanometers for our lambda max. And the actual lambda max is 232. The next one has a couple of things going on. One is that there's an alkene that is sticking outside of a ring. We call this exocyclic, being outside of the cyclic structure. And it also has 2 alkyl groups. So the exocyclic adds 5, and then each of the alkyl groups is going to add 5. And so we're going to have 217 nanometers plus 5 for our exocyclic, and 2 times 5 for our alkyl groups, and that actually ends up to be 232 nanometers as well. The actual wavelength for this one is 230 nanometers. And then the final example that we learned in OChem is the homoannular diene, which means that both of the alkenes are in the same ring. So we have an exocyclic if the alkene is outside the ring, or a homoannular system if they're both in the same and they are locked in an S-cis conformation. This adds 39, so it adds quite a bit. 217 nanometers plus 39 plus 4 times 5 for all those highlighted alkyl groups gives us 20, and our total should add up to 276 nanometers. And the actual on this is 269 nanometers. That's just the example of how we calculated approximate lambda maxes, and then you can compare them to your literature data or your experimental data. In lab, we're not going to worry too much about this. This go round will be just looking at lambda maxes and extinction coefficients. But we'll do some calculations later on when we get to the more in-depth UV-Vis. Any questions on that? Okay. Now you're just really ready for mass spec. So what are we looking at in mass spec? We have a GC mass spec on campus here, which has a gas chromatograph before where you inject it in, and then it goes through this column and it separates out your compounds, and then it detects the ions. And so we're looking at detecting individual ions. We're looking at detecting every single ion has a molecule that's going to go through the column, and then it gets to the ion source in the mass spectrometer, and the ion source is going to ionize your sample and give you the molecular ions or other ions. The one way we learn about in organic chemistry was to bombard the sample with a bunch of electrons, and that's going to help eject out other electrons and form the M+. So we use the electron beam to form cations. There are additional techniques that we'll talk about later on, but the electron beam or electron impact, which is abbreviated as EI, is the technique that we'll use on our GSA mass spec. The units for this is going to be a mass to charge ratio. So we have the mass divided by Z. You guys have seen this a few times now. Mass to charge ratio. And for the most part, our charge is going to be +1. As mentioned before, it's hard to get more than a +1 on one molecule unless it's a really big molecule, because otherwise they get pretty unstable if you put more than one charge on a molecule. As you get to larger and larger molecules, they tend to get more charges per molecule, and you actually see that fair amount when you're trying to do proteins or other larger samples like that on mass spec. But we'll look at mostly +1 charges. And so in what it's measuring, well, we already went over that, mass of the ion. You're not just going to get one ion, you're going to get several ions. You're going to get your M+, your M+1, your M+2, you're going to get some fragmentation, and so we'll review how to interpret all of those. As far as sample prep goes, typically you take your sample in a low molecular weight solvent or something that has a low boiling point. So some typical ones might be methanol, acetone, hexane, typically things that are going to be a lower molecular weight and boiling point than your solvent. In particular, on our gas chromatograph, we want them to be low boiling point because they're going to come off the column first and then separate all your compounds out and detect them. So we want to get that solvent off before we start trying to detect our peaks, or the solvent's just going to outweigh, not really outweigh, but make it so that the spectrum is just going to look like your solvent and you're not going to see the little peaks for your actual compound. Typically, these are in very dilute solutions, so you have a nanogram per milliliter solution of your sample to solvent. We are detecting individual ions, so you only need a few ions to get through depending on how sensitive your sample is. So you need more than one ion, but you don't need to flood the mass spectrometer, or it's not gonna, it builds up inside. And Jeff took ours apart over Jan term and cleaned it out. There was a lot of crusty black stuff on it from all the ions that we've been putting on it over the years. And so you want to keep that pretty clean, and it is in an evacuated chamber there, so it evaporates most of the solvent or low molecular weight stuff. And we'll get into more details on that later. But how do we interpret this? What are we looking for in the peaks? We're going to look for three things in particular. First off, your molecular ion. Which is going to be that M+. That's going to be the first thing you want to look for. Then we're going to look for the isotope peaks. And that's going to be our M+1 plus and M+2 plus. Now technically, those are M+1 plus and M+2 plus because they are positively charged ions. I tend to just say M+1 and M+2 because it gets awkward to say M+1 plus all the time. So we'll look at M+1 and M+2 to determine what kind of isotopes, and that will give us information on the elements that are present. And then number 3 is going to be our fragmentation. And those are going to be our peaks, where we have M minus some number plus, where we've taken our molecular ion and it's broken up into pieces, and we can analyze the pieces to determine what types of things were attached to that chain or ring. So 3 things we'll look at. First one is going to be our, well, I should mention our molecular ion is going to be our highest mass to charge ratio, typically on the spectrum. We also have the base peak. So the base peak is just the 100% absorbance on the spectrum. Note that this is a relative number. This is, they set the base peak as 100% and everything else is relative to the base peak. And that's calculated for you by the computer. This is all relative. Base peak doesn't tell you too much about it. It just mostly tells you what's the most stable ion that's formed from your molecule. So it could be that your molecular ion is not very stable, but some combination that fragments off becomes more stable, and that's what we see as our M+ peak, or base peak, sorry. Sometimes they're the same thing, and sometimes they're not. These 2 examples have a M+1 peak being the base peak as well, because they're the ones with the highest absorbance. So our first step is to look for that M+ peak. That's going to tell us a couple things. First off, it can tell us the molecular weight of our compound. Then you could use that to use your rule of 13 to determine how many or what are potential good formulas to use there. Now when I first start talking about mass spec, people get confused because they say, well, that's your highest peak of absorbance. But really we're looking at the one that's really big, right? And we'll talk about these M+1 and M+2 peaks on the next slide. So, first one here is at M+ equals 109. And the one on your right, M+ equals 108. What else can we gain from this? We know our molecular weight, but there's one more piece of information we can get that's different between these.
There's a nitrogen on the left.
Nitrogen. So if we have an odd mass, it means we have an odd number of nitrogens. that could be 1, 3, 5, any odd number. If we have an even mass for our M plus, we have an even number of nitrogens. And that could be 0, or 2, or 4, etc. So just because you have an even mass doesn't mean there aren't nitrogens there, but you don't have an even or an odd number of nitrogens. If you have an odd mass, you know that there's a nitrogen there because there's actually not any other combination that gives you an odd mass. And so if we look at these two structures, we have orthoamino phenol and orthocresol, which has a CH3 group instead of an NH2 group. Okay. Let's see. One word of caution, the M plus peak is not always present. If the M plus peak is not a stable molecule or ion, it's going to fragment into other peaks. So you have to be careful when you're trying to find your M plus. I try to tell you if it's not going to be there at least, but there can be little tiny peaks out there that you're not able to interpret very well. Sometimes you don't see an M plus, and we'll have to be careful about that. Questions on that? Okay. Isotopes. Do you remember this chart? We have hydrogen 1 being about 100% of your isotopes of hydrogen. The carbon is about 98.9 carbon 12 and 1.1 carbon 13. And then nitrogen and sulfur both have a small portion of an M plus 1. And so if we're looking at our M plus 1 peak, we're going to look at carbon, nitrogen, and sulfur. Carbon is going to be the most important out of all of those because we can't have a lot of carbons in there, so that's going to be the one we'll look at the most. But be aware that nitrogen and sulfur can throw us off a little bit on that. Our M plus 2 is going to tell us a little bit about oxygen, sulfur, fluorine, and bromine. But again, the two that are going to be most important here are your chlorine and your bromine. If we look at chlorine, it is 55% carbon or chlorine 35 and 25% chlorine 37. So if we were looking at our M plus and our M plus 1 peak, what kind of ratio are we looking at?
1 to 3.
I'll say a 3 to 1.
3 to 1.
If we have an M plus, it's going to be 3 times as tall as our M plus 2 peak. If we have chlorine, bromine should be what?
1 to 1.
1 to 1. So your M plus peak and your M plus 2 peak, which comes from bromine 79 and bromine 81 respectively, should be a 1 to 1 ratio when you see those. So that's what we're going to look at on the next page. We have a couple of examples there. So if we look at our M plus peak again, here's our M plus and our M plus. Now it turns out on both of these, again, the base peak is the M plus peak. Our M plus 1 peak is then going to be the next one over. Here we have an M plus 1 and an M plus 2. We can use the M plus 1 to give us some information about the approximate number of carbons. Remember that ratio of carbon 12 to carbon 13? take the ratio of our m+1 peak to our m plus peak, on this one it turns out to be 8% abundance to 100% abundance. And so we have 100% of m plus and 8% of m+1. So we can use this in our formula to determine an approximate number of hydrogen or carbons. We take the m+1 divided by the m plus times 100, and then we take this entire thing and we divide it by 1.1 for the percent abundance of the carbon-13. So 1.1% of your molecules that contain carbon are going to have a mass of m+1. This gives us the approximate number of carbons. So if we do the actual calculation, we have 8 divided by 100 times 100. That one's easy. And we divide by 1.1, should give us
7 something.
7.27, I think. Okay. So we have approximately 7 carbons. That can help guide you once you do your rule of 13. If you're looking at your standard formula, if we looked at this one, it was 108. We divide that by 13. I didn't actually do that one, so what would it be?
8.3.
8.3, so remainder. Four? Okay, so we would have C8H12 for our formula, but our m+1 peak saying that we have 7, so we would adjust the formula to that. I happen to know that this one has a oxygen in it because it's the same spectrum that was on the last slide, so I'll adjust it for that. But this is an approximate number. It's really plus or minus 1 or 2 carbons. That gives you the ballpark. You can kind of use those two tools together to come up with your molecular formula. This is the exact same structure that was on the last page. It's like ortho cresol. We could do the same thing with the m+1 peak here, but I didn't find the numbers for that because I cared more about the m+2 peak on this next one. So we have an m+1 and an m+2 that are about a 3-to-1 ratio. That indicates that there's a chlorine on this one, and this is orthochloro phenol. So our 3-to-1 ratio of our m+2 m+2 peak gives us indication that there is chlorine in the molecule. 1-to-1 ratio would tell us it was bromine. If we look at the other ones there, sulfur would have a 4.2% abundance. Sulfur 34 and 32. So if you see a peak that's a little bit bigger than you would expect, but it's not 3-to-1 or 1-to-1, you may suspect sulfur. And then your sulfur and nitrogen or oxygen are very low contributors, so they don't give much information in the m+1 or the m+2. But that oxygen, no, sulfur or nitrogen would throw off our calculation here because it's adding a little bit that's not from the C13. That's why it can be off a little bit. Right?
The sulfur ratio is supposed to be higher than 3+1 or in the
No, you would have a have an M+1, and then you might have an M+2 that's pretty small again, but yeah, 24 to 1. So it's not close to our 3 to 1 or 1 to 1. You shouldn't be confuse those. Yeah. The other thing to consider, this works really well if you have big peaks. But if you're getting small peaks and then you're looking at the M+1, there's going to be a lot more error in a smaller peak than there is in a bigger peak. And so that's why this plus or minus 1 or 2 carbons, because there's going to be more error in the relative abundance when you're looking at little tiny peaks. So be careful with those. Other questions? Yeah.
Is there something in the mass spec that we could figure out why it was aromatic?
Yes, there's a couple peaks that we will look at on the fragmentation. They're not showing up real well on these because they're phenols, and the phenols don't want to lose their OH group. But the two in the fragmentation patterns, here, if you remember, we had a benzene ring at 77. If you have a benzene with plus charge on it, it's a mass of 77. And note that that is exactly M equals 77. It's not M minus 77. And then we also have the tropylium ion, which indicates you have a toluene, which was the M plus 91. So 77 is going to be our benzene plus, and 91 is going to be our toluene plus, or we call it the tropylium ion. There you have lost one hydrogen from that carbon on the toluene. I don't have an example of one, but I'll one up here. So if we look at this, it's ethyl toluene. So we have a toluene with an ethyl group off of it. There. And we see our molecular ion. We see a fragmentation pattern there. We also see the peak at 91, so that would be a toluene ion. And then we see a peak at 77. Those, so they work for some aromatic compounds, but they don't work for all, because you saw with the phenols that it wasn't working very well with those. But they are good peaks to look for in the mass spectrum. Other ones that we looked at in organic were the M minus 15, M minus 29, M minus 43, M minus 57. Each of those corresponds to the loss of a CH3 group for a methyl, or then an ethyl, or a propyl, or a butyl. This compound here is this hex 1, 2, 3, 4, 5, 6. So a hexene molecule with 2 methyl groups on it. If we look at our M plus peak, it's at 112, and then our next one over is at 97. So that's an M minus 15 peak. Next one over here is 83. So we have an M minus 29. 69 is M minus 43. M minus 57, and then this next one's actually M minus 70. 71. Each of these corresponds with the subsequent breaking off of either a methyl group, an ethyl gives you a little bit of information about the conductivity of the molecule, so you would know that you have a methyl at the end of the chain, or an ethyl, or a propyl, depending on how it fragments. You also may recall the loss of water from an alcohol, so the M-18, and that's why we sometimes don't see the M plus peak very well, because water is really easy to lose, or the McLafferty rearrangement, which we'll get into in more detail. But the key there is that it's N minus an even number, it's not 18, because all of these are losses of odd numbers.